is the same as what you see in Punnett Square. Test cross was what I was doing last week when I was crossing um the phenotypes. I mean, when I was crossing the gametes, that was what we call test cross. So an individual with dominant phenotype could be either homozygous dominant, which you already understood what that is, but I'll do a little reminder of that now. Homozygous dominant is going to be like uppercase A, this is homozygous dominant, and then heterozygous is going to be like this. All right, that's heterozygous. So determine the phenotype, the genotype, we can carry out the test cross, breeding the mystery individual with a homozygous recessive individual. If any offspring display the recessive phenotype, the mystery parent must be heterozygous. So this is what we are saying. In essence, you are looking at a case, it's just test crossing, right? Test crossing, just like if you have this now, if you have someone that is on phenotypically, let's say the person is tall, and we feel like tall is HH, or let me use this for tall. Tall can be homozygous tall, tall can be heterozygous tall. This man is going to be tall as long as T is the tall is dominant, right? So these are both tall, but we can want to trace. We may just know the phenotype and we don't know the genotype. So if we know the phenotype, we can be tracing. Of course, it's just guess, right? To see, okay, what can be the parent, like who can be the parent of this tall guy, what can be their genotypic ratio, so that we can get the genotypic ratio of the guy. So if all the parents were true breeding, if all the parents were to be true breeding, then the child is going to be homozygous tall if both parents are homozygous tall as well. But if both parents were heterozygous tall, that means the child may have been heterozygous tall or homozygous tall. I'll just do a scenario of what I'm talking about. Just like this now, if two parents have this, and we cross them against each other, all right, we already know what the offspring is going to be like. So I'm going to do the crossing now. You cross this now. The first thing that is going to happen, of course, is that there's going to be segregation, which is what the law of segregation says, right? There's going to be segregation first, which means that they will separate first, right? So we are going to have this. So now we're going to cross it. This against this, it gives us homozygous tall. Then this against this give us heterozygous tall. This against this give us heterozygous tall. And this against this give us homozygous short. So in quotes, these three children now will be tall. But if the three children are tall, phenotypically is 3:1. Right, so phenotypically, if you look at this, phenotypic ratio is 3:1, but genotypic ratio is actually 1:2:1, because 1 is actually the homozygous tall, 2 is heterozygous tall, and 1 is homozygous recessive. So the genotypic ratios give the genotypic details, whereas the phenotypic ratio just give what you can see on the outside. Let's go. All right, so that's what you saw here. Again, this is Punnett square. It gives you the same result. Now, if you look at this parent, these two parents are homozygous purple, and then homozygous white. By the time they were crossed, okay, sorry, let me start from here. So you have true breeding parents, they gave all the these are the P generation. Then the first filial generation will be all the first filial generation now is going to be, so if you look at it, these are purple, which, let me use my annotations. Now if you look at it, these are purple, and the purple, we are saying that it may be either this homozygous or heterozygous. But of course, we know that this is always going to be homozygous white, right? Now, if they were to be homozygous, so now we want to do a prediction if it was to be this and if it was to be this. So now the first cross is for this, all right? So this is this here crossing against the white, and this is this here crossing against the white. Now, the end result is that all of the offspring on this, because these are true breeding, if you remember, we call this true breeding because both parents are true breeding parents. Now, eventually, all the offspring ends up to be purple. Phenotypically, they are purple, but genotypically, they are heterozygous purple. But here, all the offspring, two of them are purple, heterozygous purple, and then two of them are homozygous purple. All right, so those are the scenario from that if we're looking at that to just review. All right, so Mendel derived the law of segregation by following a single character. And I told you already, law of segregation simply means the allele must separate before a gene can be inherited. So the F1 offspring produced in this cross were monohybrid. Monohybrid simply means one trait. One trait. So all of the things that I've been showing you is one trait. We are just looking at, okay, the height, the color, that's just one. All right? Meaning that they were heterozygous for one character, just one character. A cross between such heterozygous is called monohybrid cross. Mendel then identified the second law of inheritance by following two characters at the same time. Take note of that. So instead of just saying color now, Mendel blended like color and shape together. So you can say purple and round, tall and slender. Those traits are marginal, two different color, two different traits. Looking at it together, that will be dihybrid. So crossbreeding two true breeding parents differing in two characters produce dihybrid in the F1 generation, heterozygous for both characters. A dihybrid cross is a cross between F1 dihybrid, can determine whether two characters are transmitted to offspring together as a unit or independently. That's what we want to look at. So looking at this, inquiry, do alleles for one character segregate into gametes dependently or independently of the allele for a different traits? So what we are saying is this here is the allele for color. Yellow, yellow is for color. And this RR is for shape. So you see that this is yellow and round. This is green and wrinkled, not round. So what Mendel wanted to check is, since these alleles are together, is it possible that they are transmitted together or they are transmitted independently, or what is the pattern? So what he did was this. He looked at this. If this is homozygous Y and homozygous R, of course, it is the simplest. What you can get from this is just, you can get this and this. Of course, that's all you can get. And that's it here. That's the gamete. All right. From here, what you can get is also this. This is the gamete. So this is what is going to go into reproduction, into fertilization, so into the offspring. So now, if you look at this, this is YYRR. This is what you see in the dihybrid organism. Two traits together. Now, crossing these two traits, if you want to get gamete from this now, this is now not straightforward like this. Because to get gamete from this now, look at it. If you have Y, Y, R, R, there are many combinations that can come out from here. Number one, you are able to see YR, uppercase. You are able to see Y, then lowercase r. You are able to see lowercase y, then uppercase r. And you are able to see lowercase y, and lowercase r. So those are the likely gametes that you can get. If you look at it, that's it. So you want to look at it very well. Those are the gametes you can get from that. When we're looking at this, if you look at this now, the first one we looked at YYRR. The gametes you can get from this is just one Y and R. There's nothing else. If you look at this, YYRR, the gametes you can get is just Y and R, nothing else. You can get 4 of them, but it's the same thing. That's all you can get. Now, so in this case, this is what he got. Then he now crossed it with each other, which is what we saw here. I'll show you the two scenarios. So he crossed this against each other, you see, against this, as though this is the sperm and this is the egg. So he crossed it, then these are the offspring that was generated. 16 of them. And so there were 9 of them that was round. 9 was round. 3 round and yellow. 9. And if you with yellow produces orange. This answer is so yellow and round. You see, this is, if you cross this and this, you see yellow round. This and this is still yellow round. This and this is still yellow round because yellow is dominant. This and this yellow round. This and this yellow round. This and this, of course, it is yellow but wrinkled. So you see yellow wrinkled. This and this yellow and round. Yellow wrinkled. So you cross it like that, you eventually have 9 that are yellow and round, 3 that are green and round, 3 that are yellow and wrinkled, and 1 that is green and wrinkled. So phenotypically, it is 9331. That is the formula. We will not ask you for genotypic ratio of this. You only care about the phenotypic ratio for dihybrid traits. Now, for monohybrid, of course, we already know that the monohybrid, we already know that phenotypic ratio is 3:1, and genotypic ratio is 1:1. But for dihybrid, we only care about the phenotypic ratio. So the other way, so this is the law of independent assortment. Independent assortment means that it does, so, okay, good. Let me look at the other one. If it were to be dependent assortment, it means that anywhere you see these dominant traits, they will always be together. So you see YR together here, and then YR, okay, then YR, then YR. So it has limits. That's all it can make. Unlike this, that is independent. So dependent means the traits are dependent on each other. Dominant goes with dominant, recessive goes with recessive. And so instead of having this variety, for dependent traits, you are just going to have these 2 instead of having these 4. So Mendel saw that this was not the case. So this is wrong. This is what is right. All right, let's go. So using a dihybrid cross, Mendel developed the law of independent assortment. Independent means it is assortment simply means to separate, to detach. So meaning that they are being separated or being transmitted to an offspring without depending on any factor. That is independent assortment. So it states that each pair of allele segregates independently of any other pair of alleles during gamete formation, meaning that one allele is not waiting for the other before it can be separated or transmitted to any offspring. They go by themselves. This law applies only to genes on different non-homologous chromosomes or those that are far apart on the same chromosome. Now, genes located near each other on the same chromosome tends to be inherited together. Take note of that. There's a term we call link genes. Genes that are closer together are usually inherited together. Mendel's law and segregation and independent assortment reflect the rule of probability that apply to tossing coins or rolling dice. When tossing a die or coins, the outcome of one toss has no impact on the outcome of the other. If you throw a dice now and you throw another one, the first one you threw does not affect the second one in any way. Every die you throw is a new toss. In the same way, the allele of one gene segregates into gametes independently of another gene alleles. It does not affect each other at all. So we call it law of independent assortment. So multiplication rule states that the probability that two or more independent events will occur together is a product of their individual probabilities. I'll talk about that. Probability in an F1 hybrid, monohybrid cross can be determined using multiplication rule. Segregation is in the heterozygous plant is flipping each coin. Now, each gamete has half chance of carrying the dominant allele. So like this, now if I have a coin and I flip the coin, there's half chance that it can be the head or it can be the tail. So that is probability becomes half. But I'm going to explain that in a bit. Now, so probability is simply we use product rule for it. Product rule simply means you multiply both probability together. All right. So you find the probability of the case that it can be the head, then find probability that it can be the tail, and then you multiply the two. But addition rule states that the probability that any one of two events or more mutually exclusive events will occur is calculated by adding. So product rule, multiplication rule, we multiply, we multiply together. Addition rule, we add together. So the rule of addition can be used to figure out the probability that an F2 plant from a monohybrid cross will be heterozygous rather than homozygous. I will explain that now. All right, cool. So when you look at this, okay, this is it. So let me just come here straight. When you look at this now, let's say we are saying what is the probability that this will happen. Okay, if you come to this image here, let me come here. So YY, right? Now, if you look at this here, let me use this. Okay, cool. So if you are looking at this one, for instance, now, and we want to look at the probability that, what is the probability that, I want to look at this to understand the product rule and the addition rule. It's straightforward. I'm going to use this to explain it quickly. So when you say what is the probability that we are going to have, please be with me. When you say what's the probability that we are going to have this and this. Now, what do we have to do? All we need to do is to check how many of these do we have. Probability that it will be, I'll just use probability PR. Probability that it will be this is equal to how many of these do we have here? We only have one of these in total, just one. So the probability of it is going to be 1 over 16 because we have 16 in total. Now, then the probability that is going to be lowercase y, uppercase r, and lowercase r is how many of these do we have? We have one of these here, we have one of these here, that's 2. So 2 is equal to 2 over 16. Now, the question is, what is the probability of this and this? So the question is, what is the probability that we are going to have this and this? So now the answer to that is actually 1/16 times 2/16. That is the answer to that question. So that in that case becomes, we calculate that, divide this by 1, 8, then 1/16 times 8. That will be the answer. Now, if the question were to be, what is the probability that is going to be this or this? You know, the probability was this and this, we multiply. But if the probability was what, if it was to be probability of this or this, then we are going to add at that time. So the addition rule is going to come to place. It will now be 1/16 plus 2/16. That will be the addition rule. Let's go. I just need to explain that a little bit. It's not something I need you to know beyond that, just what I've explained. So you see, probability that any one of two, or you see that, or more mutually exclusive events will occur is calculated by adding the total events together. All right, let's go. So that's what happened here. This is multiplication rule you are seeing here. This probability of this happening, 1/4 of this and 1/4 of this. That is what you see here, splitted out for each of them. And probability of this happening, that is done here as well. It's simply probability is adding and multiplying depending on what we are doing. All right, let's go. Now, the relationship between genotype and phenotype is really simple, as in P-plant characteristics that Mendel studied. Many heritable characters are not determined by only one gene with two alleles. However, the basic principle of segregation and independent assortment apply even to more complex pattern. I'll talk about that. Now, inheritance can be caused by a single gene, and it may deviate rather from simple Mendelian pattern in the following directions. So we want to look at this now very carefully, please. Now, when alleles are not completely dominant, what is going to happen? You know, I've told you about dominant genes. When a gene is dominant, and if a purple mates with a white flower, it gives rise to purple flower. But it's not always going to be like that. When a red flower mates with a white flower, it gives rise to red flower. Red is dominant. But there are some times when something will happen and the red may not be completely dominant over the yellow, over the white. How do we explain the case of when red and white mate and it gave rise to pink? How do we explain the situation when your dog that was black and mated a dog that was white and they gave rise to gray dog? How do we explain when a cat that was black mated a cat that was white and the new cat have both white and black on itself? You can see black on that cat, you can also see white on the cat. How do you explain that? When a dog have a head that is like black and the other part of the body is white, or when there is a side of the dog that is black and every other part is white because their parent is white and black. How do we explain all of those? So we need to talk about all of those now. When a gene has more than two alleles, how do we explain that? How do we explain when the gene produces multiple phenotypes? So let's go ahead and look at that. So there's something we call, there's degree of dominance. Dominance is not always going to be 100%. There's a point when it is complete. When it's complete, that's the case of purple and white flower mate, and then you see purple flower. That's the case of black and white dog mate, and you see black dog alone in their offspring. That is complete dominance. So complete dominance occurs when phenotype of the heterozygous and dominant heterozygous are identical. That is complete dominance. but there are cases of incomplete dominance. So you see, the incomplete dominance, the phenotype of F1 hybrid is somewhere between phenotypes of the two parental offspring. That is, parental varieties. That is the case when a dog, a white dog, and a black dog mate, and instead of the children of the offspring to all be black or white, they ended up becoming gray or harsh color. A case when a plant, a pink plant, a red plant, and a pink plant mate, and all the offspring are pink. They are not red, they are not white. In that case, we are not seeing definite color of the parent in the offspring. We are seeing a blending of the color. And so we call it hybrid. All right. So that is the case of incomplete dominance. And the case of codominance is the case when a black dog and a white dog mated and they produce offspring. And in the offspring, you can see black, you can also see white. That is not incomplete dominance, that is codominance. Both of the colors are dominating. So codominance, two dominant alleles affect the phenotype in separate, distinguishable way. You can distinguish between the colors in the parents on the offspring. So you see, this here is a red flower mating a white flower, and now we have pink flower. This is the case of incomplete dominance. Incomplete dominance. Now, by the time you see the F2 generation, this guy now mated himself, produced gamete and mated himself. Now, in the offspring, you will see different colors springing out again, incomplete dominance. Now, what is the relationship between dominance and phenotype? Of course, dominance is what determines phenotype. I'll just leave that and go straight. Dominance determines phenotype. We already talked about that. Just read that. Frequency of dominant alleles, yeah, just read that. It's just talking about the frequency, how they are frequent. Now, multiple alleles. Most genes exist in population in more than two allelic form. For example, the four phenotypes of ABO blood types in humans are determined by three alleles for the enzyme that attaches to A or B carbohydrate to the red blood cells. Now, IA, IB, and high, it simply means the blood cell have antigen A, the blood cell have antigen B, and the blood cell have no antigen. So that's why we say it's made up of multiple alleles. Now, the enzyme encoded by IA allele adds the A carbohydrate, the antigen A, whereas the enzyme encoded by B adds the antigen B. And the enzyme encoded by high does not have any of them. Now, this is what you see in that case. So the person that have blood type A, of course, only have antigen A, and blood type B, antigen B, blood type AB, antigen AB, blood type O, no antigen rather. All right. Now, in the case of pleiotropy is when you say most genes have multiple phenotypic ratios. So a gene now can have many expressions depending on where maybe other factors that could be responsible. So for example, pleiotropic alleles are responsible for multiple symptoms of certain hereditary diseases, such as cystic fibrosis in some people, sickle cell in some people, right? So in this case, we say this gene have multiple expression. That's all you need to take note on that. I'm trying to move a little fast now. Some traits also, I just told you now that a gene may have multiple expression, but one expression can also be determined by multiple genes. So a gene can have multiple expression, and we call that pleiotropy. But multiple expressions, one expression can also be determined by multiple genes, and we call that epistasis. All right, that is epistasis. This area, epistasis. This is multiple gene affecting multiple gene affecting multiple traits. One trait. So some traits may be determined by two or more genes. In epistasis, one gene affects the phenotype of another due to the interaction of their gene products. So in polygenetic inheritance, multiple genes independently affect a specific trait. So this is what I'm talking about. One gene, we call it polygenic inheritance. So epistasis, one gene affects the phenotypic effect of the phenotype of another due to interaction with their gene product. So we call it polygenic inheritance in the case when multiple gene is affecting one trait. So that means if a mother or a father is going to give that trait or transmit that trait to an offspring, the multiple gene that is affecting the offspring, the trait, will also be transmitted to that offspring. It's not the case of one gene affecting one trait. It's a case of multiple gene affecting a single trait. All right, that is what we call it polygenic inheritance. Now, epistasis, expression of a gene at a locus which alter the phenotypic expression of a gene at another locus. That is epistasis. Okay? Don't confuse it. I don't know if I flipped it earlier. Polygenic inheritance, multiple gene. So I'll take it again. Pleiotropy, a gene having many expressions. Pleiotropy. You see that in cystic fibrosis, sickle cell diseases. A gene, multiple expression. Multiple gene affecting a trait. That is polygenic inheritance. Polygenic, many gene affecting a trait. Epistasis is when the expression of one gene at a locus, you remember locus, the location of a gene on a chromosome. The expression of one gene is also affecting the expression of another gene that is on another locus. For example, in Labrador retriever and many other mammals, coat color depends on two genes. So one gene determines the color pigment, allele B for black and B lowercase b for brown. The other gene with allele E for color and lowercase e for no color determines whether the pigment will be deposited in the hair or not. So look at it here. All right, this is what we are talking about. All right, so if heterozygous black genotype BBEE are mated, we might expect that ratio. All right, so that's what you see here. Epistatic interaction produce a variety of ratio, all of which are modified versions of this. So that's what you see here. Different genes, a gene having an impact at one location affecting the expression of another gene at another location. In essence, this is it. There may be a gene for this color, and then there's another gene that regulates the expression of the color in another area. So multiple gene just having one effect, because the overall thing is the color now, but you see there are different variations of the color, even though it wasn't the case in the parent. Now, quantitative characters are simply characters that you can quantify, you can measure. Then qualitative are the ones that cannot be measured, they can only be evaluated. All right, so when you say quantitative character, you'll be thinking of height, you'll be thinking of weight, you'll be thinking of things that you can measure. Temperature, those can be measured. But if you are looking at pain, for instance, that would be quantitative. All right, so generally when we come to characters as well, we talk about quantitative character and qualitative characters. Let's go. So I'm just focusing on things that I feel I still need to explain now. Okay, no. All right. I would talk about pedigree. Then I want to see. Okay. All right. So let's go ahead and talk about pedigree. Now, A pedigree. All right. Now, a pedigree simply means it's like a family tree. That's a simple word to use. Think about if you want to trace your family from you and you now want to go up the ladder and go to your parents, to grandparents, great grandparents, as many that you can remember. That you can trace. That is pedigree. So a pedigree tells you the likely genotype or phenotype. You can use that to trace the like. If you know the phenotype, you know anything of one, you can use it to trace the likely. Let's say you know the genotype, your genotype now, you know that of your parent genotype, then you can use that to trace the likely parent, grandparent, grand great grandparent, and go that way and say and make a likely prediction of their genotype. That is pedigree. So in human genetics, geneticists analyze the results of human matings that have already occurred. A pedigree is a family tree that describes the inheritance pattern. It describes the inheritance pattern of a trait across generation. That is a pedigree. So if you look at this now, you see this trait here. So this gives you the key. It tells you that this so it tells you that this is a male child. When you see this, it means a male. When you see this, it means female. This means male with a trait or male with a disease. This means female with a disease or with a trait. Now, when you see this, it means that the females are mating, husband and wife. When you see anything like this, it shows that they are offspring. So horizontal line like this means mating. When you see this that looks like this is offspring. Now, sometimes we also use this either halfway shaded. Halfway shaded could be that I'm still going to use that later in the next upcoming chapters. Half shaded could mean that somebody have a disorder, somebody have a disease. All right. Or we can also use this for that. Now, sorry, it doesn't mean it means somebody is carrying the disease. So there's a difference between carrying a disease, which we call carrier, and having a disease or symptoms is different. Somebody can carry the disease and not have symptoms. The person that carried the disease does not have symptoms, we use this symbol for it, either of these two, for female. It means the person is carrying the disease, but the person is not affected by the disease. Okay, so we'll talk about that more. All right, so if you look at this now, this means this person has a trait that we are talking about, that we are focusing on. That's the first generation. By the time the first generation give birth to children, they have two of the children have the trait, the other two does not have the traits. And you notice that males, one male have the trait, one female have the trait. That tells you that if you look at, let me use my annotation.